What if I told you that the smallest engine ever built is so tiny, you could lose it between your fingers? And the biggest engine ever built is so massive, it has its own floor plan. We talk a lot about power in the automotive world, but those conversations almost always happen in the middle of the scale. The comfortable range where cars live, where engines are something you can picture, something you can relate to a garage or a racetrack or a road. Today we're going to the edges, both of them, at the same time. Let's start small, impossibly small. In 2003, researchers at the University of California, Berkeley, built what was then considered the world's smallest engine. It was found under a microscope. The device, called a nanoengine, measured just a few nanometers across. To put that in perspective, a single human hair is roughly 80,000 nanometers wide. This engine was smaller than most bacteria, but it worked. It converted energy into motion at a scale so small that the physics governing it are completely different from anything you'd find in a garage. At the nanoscale, the rules change. Engineers working at this scale aren't fighting friction the way a car engine does. They're fighting quantum effects. They're building machines where a single misplaced atom can change how the whole thing behaves. The fact that it works at all is extraordinary, but that's almost too small to feel real. So let's talk about something you can actually hold. The Cox Thimble-Drome .049, introduced in 1947. This is the smallest mass-produced combustion engine ever made, and it is legendary. The .049 refers to its displacement, 0.049 cubic inches, less than 1 cubic centimeter of engine. It weighs less than 2 ounces. You could fit it in the palm of your hand with room to spare, and yet it runs. A single cylinder, a single moving piston, a glow plug instead of a spark plug, a fuel mixture of methanol, nitromethane, and oil. When you flick the propeller to start it, the engine catches, and what comes out of it is one of the most distinctive sounds in mechanical history. A high-pitched, angry, wasp-like scream that seems impossible for something that small to produce. The engineering tolerances on the Cox .049 are absurd for something made in the late 1940s. The gap between the piston and the cylinder wall, called the clearance, is measured in 10,000ths of an inch. They were doing it by hand with gauges and experience at a scale that would be challenging even today. At full throttle, the Cox .049 spins at over 30,000 revolutions per minute. For comparison, most car engines redline somewhere between 6,000 and 8,000 revolutions per minute. This thing, smaller than your fist, is spinning nearly 5 times faster than a performance car engine at its absolute limit. That speed creates its own problems. At 30,000 revolutions per minute, the forces acting on that tiny piston are enormous relative to its size. Everything has to be right, every single time, for an engine that costs less than a pair of shoes. It powered model aircraft throughout the 1950s, 60s, and 70s. Generations of kids learned what an engine was by holding one of these in their hands, feeling the vibration travel up through their fingers, hearing that unmistakable sound tear across an empty field. There is something almost emotional about the Cox .049. It is the engine that taught people engines were possible. It is a near-perfect engine, simple, reliable, wildly overpowered for its size, and it weighs less than a golf ball. Now we go in the other direction. The Wärtsilä RT-flex96C. It doesn't sound like an engine. It sounds like a classified government project, because what this machine represents is the absolute outer limit of what human engineering has been able to achieve in mechanical power generation. To understand why this engine exists, you have to understand the problem it was built to solve. The global shipping industry moves approximately 90% of everything traded between countries, and container ships are only economically viable if they can move enormous quantities of cargo as efficiently as possible. That means one thing above all else: you need the most powerful engine you can possibly build, running as continuously as possible, for as cheaply as possible per unit of cargo moved. The RT-flex96C is the answer to that problem. Built by the Finnish company Wärtsilä, the RT-flex96C is a 2-stroke turbocharged diesel engine. It was designed for one purpose: to power the largest container ships on Earth across the world's oceans. It is 89 feet long, nearly as long as a standard NBA basketball court. It stands 44 feet tall, roughly 4 stories. It weighs 2,300 tons. That's 2,300 metric tons of steel, pistons, crankshaft, and engineering precision assembled into a single machine. It has 14 cylinders. Each cylinder has a bore, the diameter of the piston, of 96 centimeters, nearly a meter wide. Each piston alone weighs over 5 tons. The crankshaft weighs 300 tons by itself. At full power, the RT-flex96C produces 107,390 horsepower. For context, a Formula One car produces around 1,000 horsepower. This engine produces the equivalent of over 100 Formula One cars firing simultaneously. all connected to a single shaft. It burns approximately 1,660 gallons of fuel per hour at full load. That's roughly a gallon every 2 seconds. The fuel it burns isn't the refined diesel you'd find at a gas station. It's something called heavy fuel oil, a thick, viscous byproduct of petroleum refining that looks more like tar than fuel and has to be heated to around 150 degrees Celsius before it can even flow through pipes. The engine turns its output shaft at 102 revolutions per minute. 102 revolutions per minute, slower than a ceiling fan on its lowest setting. The force it generates at that speed is so immense that the engineering challenge isn't making it go faster. It's making the materials strong enough to survive what's already happening at 102 revolutions per minute. The crankshaft alone flexes measurably under load, not because it's weak, it's 300 tons of forged steel, but because at this scale, under these forces, everything flexes. The engineers who designed it had to account for that flex in the alignment of every bearing, every journal, every surface that touches another surface across 89 feet of rotating machinery. The ship it powers, the Emma Maersk-class container vessel, is 1,300 feet long and can carry over 14,000 shipping containers stacked across its deck and holds. When it moves through water at its cruising speed of 25 knots, that single engine below deck is doing all of it. Every ton of that moving ship, it runs continuously for months without stopping. There are no pit stops. There is no idle mode. It runs. So let's put these two things side by side for a moment. The Cox .049 and the Wärtsilä RT-flex96C. One fits between your fingers. One has an internal staircase. One weighs less than 2 ounces. One weighs 2,300 tons, roughly the same as 350 African elephants. One produces fractions of a horsepower. One produces 107,390. One spins at 30,000 revolutions per minute. One spins at 102. One sounds like an angry wasp. One sounds like the earth itself shifting, a deep, rhythmic, subsonic pulse you don't hear so much as feel in your chest and your bones and the fillings in your teeth. And here's what is remarkable about both of them. They work on the same fundamental principle. Fuel ignites, gas expands, a piston moves. That motion is converted into rotational force. Whether the cylinder is the size of a thimble or the size of a room, the physics are identical, separated by a factor of approximately 1 billion in scale, but fundamentally, mechanically, the same idea executed at opposite ends of what's physically possible. The engineers who built the Cox .049 were obsessed with miniaturization, with how small they could go before the tolerances became impossible, before the heat became unmanageable, before the fuel couldn't flow fast enough through passages thinner than a human hair. The engineers who built the RT-flex96C were obsessed with the opposite, with how large they could go before the materials failed, before the vibration tore the structure apart, before the forces involved exceeded what metallurgy could withstand. And both teams built something that runs. What connects every engine ever built is that somebody looked at a problem and decided the answer was combustion, controlled explosion. That idea, that simple, stubborn, violent idea, built the modern world. Engines are not just mechanical devices, they are arguments. Arguments made in steel and fire, that a problem has a solution, that something can be made to run that has no business running at all. The smallest engine ever made makes a sound like tearing paper at 30,000 revolutions per minute in the palm of your hand. The biggest engine ever made makes a sound you can feel 3 decks above it, standing on the hull of a ship the length of 4 city blocks, in the middle of an ocean with no land in sight. Both sounds are perfect. That's red line verse.